Hello everyone. In today's session, let us see how a Xilinx coding, that is a Verilog coding, can be implemented using FPGA kit. Okay, so let us go with the procedure. Go to File, click New Project, right? So give a name. Let it be some demo 2, and in the location C:, the Xilinx folder, we are just creating a project as demo 2, right? Check whether the top level source type is selected as HDL. Click next, and next to that we have to check whether the family is Spartan 3 and the device we are having is XC3S400 with a package of TQ144 and the speed is set as -5, right? And also ensure that the synthesis tool is a Verilog or VHDL and the simulator is ISC simulator, right? Click next. Now we have to create a new source file. So let the source file be a Verilog module. Okay, so let the name of the module can be demo 2. It need not be the same as that of the project name. You can give some other name also. Okay, and make sure the location is C:, Xilinx within the same project we have saving. Next, and now we are going to give the input A, B, sum, carry, right? In which A and B are going to be the input, sum and carry are going to be the output. Click next, finish, next, next, finish. Right. So you will be getting a page like this. Okay. So this is the very start of your Verilog coding. You will be having the module followed by the file name, right? So then within the bracket you will be having the first two terms or your input, and sum and carry are going to be the output. So that is being declared here, right? Now we are going to type our program, right? The first one is, this is for a half adder, okay? So we have given the input as A and B and the output is going to be sum and carry, okay? So first one is, we are going to make a XOR operation, okay? Where the output is going to be same in sum, the inputs are going to be A, B, right? Similarly, we are going to perform a AND operation in order to find out the carry using the inputs A and B, right? Okay, so we have written it. So go to File, Save. Then coming to this user constraint, we have to assign the package pins. So assign the package pins in the sense we have to go for the device architecture. Okay. So for that we have to assign whichever port is relevant, whichever port is being assumed as the input, and whichever port we are going to take as the output. Okay. So here we are having a specific port number list for the specific device. So we can refer it quite from the data sheets. So according to the device what we are using, that CS 400, we are having the input location ranging from P86 and 87. Okay, so let me give the input as P86. P76 will serve as the input port. P77 is one other input port, and we are assuming P86 as one of the output and P87 as another output, right? So it will be changing depending upon the device what we are utilizing. Okay, so those things will be aligned up here. Give, save. Okay, so let it be in the Verilog default itself. Click OK. Just minimize this device architecture. Okay, coming back to our Xilinx home page, and the next to that we are going to click on the synthesis XST. I just want to check the syntax error if any. So if any error comes, in the sense we are in a position to rectify that error. Okay, so now we are checking the syntax. Our process check syntax is completed successfully, right? And then we have to come up for the implement design. So in the implement design we are having translate. Okay, so our codings are going to be translated and it is going to be mapped with that of the input and the output put, and after that it is going to make down the wiring, that is the place and route informations will be updated. Okay, so let us wait for a moment until this process completes. Yeah, it is completed now. Then coming to the generate programming file. Now we are going to configure the device. Okay, so before going into that, let us see to that device. Okay, so what is the device we are having? Right, so this is our FPGA kit. Okay, and this is the peripheral device. Okay, so this FPGA kit is connected to our CPU using this cable, and this FRC1 is connected to the dip switch where we are going to give down the input. Here we are having 8 number of dip switch. Depending upon the position of the dip switch, we can verify the output in the corresponding LED. Therefore, this LED is being connected to this FRC2. Okay, here we are making use of this Spartan 3 model, and this is our FPGA kit. This is our peripheral unit. Right, let us come back to the configure device. Right, in the generate programming file, we are having a configure device. So let us click it. Okay, it is being initiated. The process is being initiated. So once it is initiated, we will be getting a new tab over that. Okay, so that is the impact tab, and here we can set the condition. Automatically connect to the cable and identify the boundary scan chain. So if else, we need to give manually fixing this boundary scan chain. Okay, click finish. Right, so since some other program is being executed in the same, I'm just giving up this bypass option, and this is the Verilog file actually we have created. Now it is saved in the form of .bit file. Okay, so click over that. So before that, you could see the Xilinx device does not have any other file. So once I click over this demo2.bit, you could see the demo2.bit is loaded into our Xilinx. Right, now right click, program, apply. Okay, so let us wait so that our coding is being transferred to our FPGA kit. So if you are having any errors or warnings, we will not be getting this. Yeah, our program is succeeded. What does it actually mean in the sense? The coding, whatever we have written in demo2.bit, actually we have written a coding to implement half adder. So that is being transferred to this FPGA kit. Okay, now let us see how the input is going to be varied and the corresponding variations in the output. Yeah, so in the assigned package pins, we have assumed P76 and P77 as our input port. Okay, so that is, I have left the first pin as inactive. The second and the third switch are being utilized. Okay, so this is switch number 2 is used as P76 port, that is our A input, and switch number 3 is port number 77, that is being used as the input B. Right, now coming to the LED. Okay, here also I have left the first LED, and we are going to verify the output at LED 2 and LED 3. Okay, so one is P86, the other one is P87. Okay, so it's going to give the sum and the carry output. Okay, so let us change. Okay, now we are having the 0 0 input. Okay, now let us see what happens when we are going to change the dip switch. Right, so now we are going to give the input as 0 and 1. Right, I have given the input at 2 is 0, input at third switch is going to be 1, and hence I am getting the sum as 1 and carry as 0. Right, now let us go for 1 and 1 condition. Okay, if 1 and 1 is enabled, you could see sum as 0 and carry as 1. Okay, so just by varying this dip switch, if I am varying it from 0 and 0, it will remain in the 0 0. Both the sum and carry will be 0. If I am going to keep 1 and 0, your sum is 1, carry is going to be 0. If both the things are going to be 1, what happens? The sum becomes 0 and carry becomes equal to 1. Yeah, that's why we have verified the truth table of the off adder. Okay, so just what we have done, we have just written a Verilog coding that has been transmitted to this FPGA kit. Okay, so actually our coding is being transferred, it is being inserted to this kit. Okay, and after that we are just going to use this peripheral unit to give the input and to verify the output. Okay, so for we can use this FPGA kit in order to implement was whatever the thing experiments like adders, counters, shift registers. Okay, so depending upon our need and applications, we are just going to write down the Verilog coding and we can embed the coding in our FPGA kit so that we can give the input on our own and visualize the corresponding output. Hope you understand this session. Hope you all meet in the next session. Thank you.